Hey everybody, Mrs. Mancuso, some more Regents Chemistry Review. This one is going to be all about potential energy diagrams. So I need to use Table I. Table I, grab my reference table. Here we go, Table I. Table I is going to tell me the heat of different reactions. And when you have a reactions, there are some reactions that produce energy. That means they're exothermic. They release heat. Or they can be endothermic. That means they require energy and they absorb heat in order to occur. So let's get right off to some diagrams. So if this is my potential energy, and I start right off with, this is 10, 20, 30. I'm going to do this to make the math nice and easy for us. 70, 80, 90, 100. Okay, let's say that I start off with my reactants having an energy of 20. So here's my reactants. And then I start adding energy in, and I go all the way up to here. And then my molecules react, and here's my product. So wherever you end, this is going to be the energy of the products, okay? So my reactants have an energy of 20. My products have an energy of, where did I go to, 60. All right, so I can calculate, first of all, my delta H. Delta H is equal to P minus R. So I go like this. The difference between where you end and where you start is equal to the heat of the reaction. So P minus R is equal to delta H. So I ended at 60 minus 20. My delta H is positive 40. A positive value tells me that I have an endothermic reaction. It had energy that had to go in. My products ended with more energy than my reactants. Now, the energy going in to get this reaction going went from here to here. So that's 90 minus 20. So my activation energy is equal to 70. Let's say this potential energy is equal to kilojoules. All right, so I needed 70 kilojoules of energy to be added for this reaction to get started. And then I made my products. So if I wanted to write out my reaction, let's say my reactants are A plus B. I would have to add 40 kilojoules of energy before the arrow because this is an endothermic reaction. And let's say my products are C and D. That would be my reaction. So this is how an endothermic reaction looks. Now let's do an exothermic reaction. If you have an exothermic reaction, you are releasing heat. So when I do my diagram for this, I start out with a reactant that has a lot of energy. I go up and then I go down like this. So let's say again, this is 10, 20, 30, 40, 50, 60, 70. This is my potential energy in kilojoules. This is over time. All right, where I start, this is my reactants. So my reactant energy is 50. Where I end, this is my products. My product reactant my product energy is 20. The difference between where I end and where I started, that's my delta H. So 20 minus 50 is equal to negative 30. Negative tells me that this is an exothermic reaction. This is releasing heat. All right, my activation energy is how much I need to get to the top. So my activation energy here is 20. And so my reactants, A plus B, makes C plus D, plus I would make 30 kilojoules of energy. They go on this side because the energy is released. This downhill is showing me energy is going out. To figure out how much energy went out, where I end minus where I started, 30 is how much energy was released. So that's how an exothermic reaction looks. So if you look back at Table I again, all of these values. If it's negative, it tells me that my curve is going to be like this and that energy is released. And if instead it's positive, my curve is going to go up. Now, the last thing I want to show you with these potential energy diagrams is the effect of a catalyst. I always start with the exact same energy. A catalyst does not change my reactance. My reactance is the same. My delta H is the same. What changes is up here, my activation energy. I don't have to go as high. I can actually go a little lower, and I can get to product sooner. So now my activation energy is only 10. So if I lower the activation energy, I've provided an alternate pathway for this reaction that has happened quicker. So that's the effect of a catalyst. So sometimes on part 2, they have you draw in a dotted line to show the effect of a catalyst. Start at the same place, end at the same place, but don't go up as high. Don't add as much activation energy and end sooner. Thanks for joining me.